In this problem, we have a vertical straight wire with current I. So because there's current in the wire, it creates a magnetic field. The magnetic field direction can be determined with the right hand rule. If you align your right thumb in the direction of the current, which is pointing upward, on the left hand side of the wire, the magnetic field is out of the page, and on the right hand side, the magnetic field is into the page, and that is what we're interested in this problem. What's the magnitude of the magnetic field? The magnitude changes with the distance from the wire. It's equal to mu 0 I divided by 2 pi r. So it's inversely proportional to the distance from the wire. In addition, we have a rectangular loop like shown in the picture in the plane of the page, and the loop is being pulled towards right. Now the loop's dimensions are given. The vertical side is of length b, and the horizontal side of the rectangular loop is of length a, and the distance between the straight wire and the loop is r. So that's the distance between the straight wire and the left side of the loop. So that's the variable r, and the loop is being pulled at a constant speed v. We'd like to determine the magnitude and direction of the induced EMF in the loop as it's being pulled to the right. To determine the induced EMF's magnitude, we are going to use two different methods. First, we're going to use Faraday's law. Faraday's law says the magnitude of the induced EMF is equal to the absolute value of the time rate of change of the magnetic flux through the loop. In this problem, the magnetic field magnitude is not constant, but it's inversely proportional to r. So as you go away from the straight wire, the magnitude of the magnetic field decreases. If the magnetic field changes with the distance from the straight wire, how do we calculate the flux through the rectangular loop? We can set the flux equal to b times a times cosine theta this time, because b is changing. So instead, we can take an integral of b over the area of the loop. Now imagine dividing this rectangular area into vertical thin slices. Here's one such slice, or an area element. Because the area element is a thin stripe that is vertically oriented, within this area element, the magnetic field is more or less uniform, and it's equal to mu 0 I divided by 2 pi times the distance between this area element and the straight wire. The magnetic flux through this area element is equal to the magnitude of the magnetic field at the position of this area element times the area of the area element. So what is that area? This is a rectangular shape. The height of the rectangle is b, and the width is dr. So the area element dA is equal to b times dr. The magnetic flux through this unit area is b dot dA, and the total flux through the loop is the integral of b dot dA. In the next step, we substitute the formulas for b and dA. Also note that because the magnetic field is perpendicular to the area of the loop, vector b and vector dA are parallel, so the dot product reduces to b times dA. B is mu 0 I divided by 2 pi r. R is the distance between the straight wire and the area element. Now, instead of r, I'm using r prime for my integration variable because I use r, lowercase r, for my lower and upper bounds. So r prime runs from r to r plus a. That basically spans the rectangular loop from left to right. And I'm multiplying b times dA. dA is b times dr prime. This is a fairly straightforward integral. We have a lot of constants, and we're basically integrating 1 over r prime over dr prime. The integral of 1 over r prime is ln of r prime. So let's go ahead and take this integral and then evaluate it at the lower and upper bounds. Here's the result of our integral. Again, we get natural log, and we evaluate it from r to r plus a. and that way we're able to obtain an expression for the total magnetic flux through the rectangular loop in terms of r, the distance from the straight wire. Now we can go ahead and apply Faraday's law. The magnitude of the induced EMF is simply equal to the time derivative of the magnetic flux that we calculated above. So let's take the time derivative of the expression that we came up with. Here in this line, we're taking the derivative. The derivative of ln r plus a is 1 over r plus a, and the derivative of ln r is 1 over r. Now, because r changes with time, since the loop is being pulled, r increases with time. We also need to multiply this by dr dt. Also note that I added absolute value signs here because we're really looking for the magnitude of the EMF, so the expression on the right hand side should be positive. Now note that dr dt is the speed at which r is increasing, at the speed at which the distance between the straight wire and the loop is increasing, and that is equal to the speed at which the loop is being pulled to the right, and that's simply equal to the constant speed v. So in the last line, I replaced dr dt with v, the speed at which the loop is being pulled. Also in the last line, I reversed the order of the terms in parentheses to keep the overall expression positive, because 1 over r is a larger value compared to 1 over r plus a. So this is the induced EMF in the loop as it's being pulled to the right. Next, let's recalculate the induced EMF in the loop by calculating the motional EMF in each segment of the loop separately and sum all the values. The motional EMF for a given segment can be calculated by doing L times V times B, where L is the length of the segment, V is the speed at which it is moving, and B is the magnitude of the magnetic field for that segment. Let's also determine the direction of the motional EMF. The direction of the motional EMF is determined by doing, so that's in the direction of V cross B. So let's apply the right hand rule. Align your right hand in the direction of V, and then curl your fingers into the page in the direction of B. Your thumb is pointing in the direction of the motional EMF, which is pointing up. So for all these segments, this is something that's independent of the segment. It only depends on the directions of the velocity and magnetic field vectors. The motional EMF is pointing upward. Now, if you think about it, that's a meaningful EMF only for segments 1 and 3, because those are the segments that are oriented vertically. Since segments 2 and 4 are horizontal segments, a vertical motional EMF will have no effect on those segments. It will not have any contribution to the loop's overall EMF. Therefore, we set these equal to 0, EMF from segment 2 and the EMF from segment 4, these are equal to 0. Here I have substituted the formulas for motional EMF for segments 1 and 3. That's B times V times capital B. B is the length of these segments, lowercase b. V is the speed. Capital B is the magnitude of the magnetic field. I am keeping the labels 1 and 3 for the magnetic field because the magnetic field at the location of each segment is different. Remember, magnetic field changes with the distance from the straight wire. Note that I have a negative sign in front of the second term. That's the EMF from segment 3. Why is that? Let's think about the directions again. The EMF directions are pointing upward for both segments. So for segment 1, that creates a clockwise EMF in the overall loop. And the EMF pointing upward in segment 3 is creating a counterclockwise EMF for the overall loop. So here I'm picking clockwise as my positive direction. So then the EMF from segment 1 is positive and the EMF from segment 3 is negative. In the next line, I factor out the common terms, lowercase b and v. And then here I substitute the formula for the magnitude of the magnetic field for each segment. Segment 1 is at a distance r from the straight wire, so the magnetic field is equal to mu 0 I divided by 2 pi r at the location of segment 1, whereas at the location of segment 3 we have mu 0 I divided by 2 pi times r plus a, because segment 3 is at a distance r plus a from the straight wire. And then we factor out the remaining constants. We end up with the same result as before when we applied Faraday's law. Now let's determine the direction of the induced current in the loop, again using two different methods. First, let's use Lenz's law. Now let's think about the existing magnetic flux in the loop. The magnetic field is pointing into the page, so the flux through the loop is into the page. As the loop is moving away from the wire, the flux decreases because the magnetic field strength will decrease. Because the flux is decreasing, the loop's response will be to create a magnetic field in the same direction as the existing magnetic field to compensate for the loss in flux. So then the loop will try to create a magnetic field into the page. That is the direction of the induced magnetic field. If the induced magnetic field points into the page, then the current required for that magnetic field points clockwise. How do I know that? Align your thumb into the page in the direction of the induced magnetic field. The direction of your fingers, the curling direction of your fingers, show the direction of the induced current, which is clockwise. So that was Lenz's law. Now let's determine the direction of the induced current by thinking about the direction of the magnetic force acting on positive charges, because the direction of the force acting on a positive charge is the same as the direction of the current in a given wire. So how do I determine the direction of the force? Magnetic force is charge times V cross B, and these are positive charges, so the direction of the magnetic force is the same as the direction of V cross B. Align your right hand to the right following the direction of V, the velocity vector. Curl your fingers into the page in the direction of the magnetic field vector B. Your thumb is pointing up. So the magnetic force on positively charged particles is pointing up, and that is true for every segment. Because the magnetic force acting on positively charged particles points upward, only the vertically oriented segments will contribute to the induced current, and the horizontal segments will not contribute, because in a given segment we need a force along the direction of that segment for there to be a current in that segment. Plus, the left-hand side segment has a stronger force acting on it compared to the right-hand side segment. Why is that? Because the left-hand side segment is closer to the straight wire, so the magnetic field is stronger at the location of the left-hand side segment. So the force acting on the particles in the left-hand side segment has a greater magnitude than the force acting on the particles on the right-hand side segment. So the left-hand side segment is contributing to the clockwise induced current, whereas the right-hand side segment is contributing to the counterclockwise induced current because it's on the right-hand side. And overall, since there is the induced current from, or the force in the left-hand side segment is stronger, the overall induced current will be determined by the left-hand side segment, and it will be in the clockwise direction. This is consistent with the results that we got applying Lenz's law. Now let's see if our result for the induced EMF magnitude makes sense for these three special cases. In case 1, the loop is stationary. In other words, V is equal to 0. If V is equal to 0, then the EMF is going to be equal to 0. Is this expected? Yes. If the loop is not moving, then the flux through the loop will not be changing. In that case, if the flux is not changing, then there will be no induced EMF in the loop. So this is consistent. In case 2, the loop becomes very thin. In other words, A approaches 0. If A is equal to 0, then what happens to the term in parentheses? We get 1 over r minus 1 over r, which is 0. So again, the EMF becomes equal to 0. Now, physically, does this make sense? Yes. If the loop is really thin, such that A is negligible, really small, or is practically equal to 0, then there will be no flux going through the loop, so there will be no flux to change to create an induced EMF. So we do expect the EMF to go to 0 in this case as well. And finally, in case 3, the loop goes very far away from the straight wire. In other words, R becomes very large, or R approaches infinity. If R approaches infinity, 1 over R approaches 0. So again, we expect the EMF to go to 0. Physically, does this make sense? The answer is yes. When R is really large, as R goes to infinity, the magnetic field goes to 0. So there will be no magnetic flux to change, and the EMF also goes to 0.